Hi everyone, this is Julia Faith working as an assistant professor in IT department, SA Engineering College. Today we are going to discuss about synchronization in operating system. Let's see what is synchronization. In operating system, synchronization ensures that the processes should be executed in a coordinated and orderly execution manner, which will prevent conflicts and inconsistency of data where there is a shared resources. When many processes are trying to access the shared resources, this synchronization process will avoid data inconsistency and it will avoid conflicts. When it comes to the definition of process synchronization, it says that many processes can share the same memory space, or it can be managed by an operating system. It helps to maintain the consistency of data and it helps to avoid conflicts, and also this will allow only one process to make changes in the shared memory at a time. This is the diagram for synchronization process. Here, many processes are trying to access the shared memory. The processes are process 1, process 2 and process 3. Here, these three processes are trying to access the shared memory. In this, only one process called process 2 can make changes in the shared memory, where the other process can able to access the memory only in the read-only mode. Next comes to the advantages of synchronization. Synchronization is mainly used to regulate the access of the shared resources. It is mainly used to access the critical code or data sections, which will prevent the situations like race conditions and deadlocks. So this is the first advantage of synchronization, which will avoid race conditions and deadlocks. Second one is here, certain mechanisms are used which will enable the process to communicate and synchronize their activities and maintain the system integrity. Next comes to the features of synchronization in operating system. The first feature is mutual exclusion is used to prevent data corruption. So to prevent data corruption, mutual exclusion mechanism is used. Second feature is it enables mechanisms such as semaphore and mutexes. Third one, protection of a critical code from concurrent accesses. And the fourth feature is will use certain prevention algorithms to avoid deadlocks. Next comes to the types of synchronization. We have two types of synchronization here. One is competition synchronization and another one is called as cooperatively used synchronization. This is the diagram for synchronization types. Here there are two types. One is independent and another one is cooperative, and this shows how the process gets executed in two ways. One is this can be executed in a concurrent manner or it can be executed in a parallel manner. So this is the type of process synchronization in operating system. Now we'll see what is a competitive synchronization. In this, if two or more processes are said to be in competitive synchronization, if and only if they compete or they contest for the accessibility of a shared resources. If two or more processes are trying to access the shared resources at the same time, that type of synchronization is called as competitive synchronization. The example for this one is when process A and process B are trying to update the value of a shared variable C simultaneously at the same time. So this is called a competitive synchronization. Here this competitive synchronization will lead to a process called inconsistency and loss of data. Due to this competitive synchronization, we may enter into a process called inconsistency of data or loss of data. Second one is cooperative synchronization. In this cooperative synchronization, two or more processes are said to be in cooperative synchronization if and only if they get affected by each other. That is, the execution of one process will affect the execution of the other process. Example for this one is producer-consumer problem. In producer-consumer problem, if the producer produces the values, then only the consumer can able to consume it. If the producer is not able to produce it, then the consumer will not able to consume the data, will not able to consume it. So here, the execution of the producer will get affected by the execution of the consumer. So this type is called as cooperative synchronization. Due to lack of this synchronization, it may lead to a deadlock process. Next comes to the critical session. Critical session is the portion of a program where shared resources are accessed and updated. So this is the main session which is used to allow the process to enter into a critical region and to access the shared resources. Next comes to the non-critical session. Here, the shared resources are not accessed, or we can say that the shared resources are accessed only in a read-only mode. So this is called a non-critical session. So here we have studied two things, one is critical and another one is non-critical. In critical we can able to access the resources, whereas in not critical we cannot able to access the shared resources, and we can also access it only in a read-only mode. So a process can enter into a IPC environment, means inter-process communication environment. It may involve a series of critical session and non-critical session. Next comes to the race condition. Here race condition is nothing but a processes that must be racing either in competitively or cooperatively to access the critical session. So to access the critical session, each and every process must enter into a condition called race condition. The final result of this will depend on who update the critical session first or last is known as the race condition. Next is called as preemption. Here a process gets executed in the middle of other process. Next is mutual exclusion. Here when one process is in critical session, then no other process is allowed to enter into the critical session unless the first process completes its execution. This is called mutual exclusion. Next comes to the question session. Here the first question is about critical session. A critical session is a program segment, and the options given are which should run in a certain amount of time, which avoids a deadlock, where shared resources are accessed, which must be enclosed by a pair of semaphores, operations P and V. And this, the first one is it should run in a certain amount of time. No, it's not an answer. Second one, this critical session will avoid deadlocks. That is not an answer. Third one is using critical session we can access the shared resources. So the shared resources are get accessed only in the critical session. So this is the answer for the first question, and the option is C. Question number 2 is, when the result of a computation depends on the speed of the processes involved, that is said to be, option A is cycle stealing, option B is race condition, option C is a time lock, and option D is a deadlock. The answer is race condition. Here the question says that the computation depends on the speed of the process, means the computation will get finalized only by the order of its execution. So the order of execution gets completed using the process called race condition. Question number 3 is a solution to the dining philosopher's problem which avoids deadlock is 2. So here we have to find the solution for avoiding deadlock using the mechanism called dining philosopher's problem. We'll see the first situation. The first situation is ensure that all the philosophers pick up the left fork before the right fork. If the philosophers pick up the left fork before the right fork, this may lead to deadlock. So this is not the answer for this question because this will lead to deadlock. Our condition is to avoid deadlock. So we'll move on to the second option. The second option is ensure that all philosophers pick up the right fork before the left fork. So this is the vice versa of the first option. This option also leads to deadlock. So this is not the correct solution. We'll move on to the third one. The third option is ensure that one particular philosopher picks up the left fork before the right fork and that all the other philosophers pick up the right fork before the left fork. Means that this is the possible solution which will avoid deadlock. So this is the correct option when one particular philosopher picks up the left fork before the right and the remaining all the philosophers have to pick up the right fork before the left one. And the last option is none of the above. The correct answer for this question is option C. So that is used to avoid deadlock. Question number 4 is consider the methods used by processes P1 and P2 for accessing their critical sessions whenever needed as given below. So here we are going to use process P1 and process P2 and we are going to access the critical sessions by using two methods. Here the initial value of the shared Boolean variables S1 and S2 are randomly assigned. Boolean values in the sense here the Boolean values assigned to the variable S1 and S2 can be 0, 0, 0, 1, 1, 0, 1, 1. So this is the options for Boolean values for a shared variable S1 and S2. So first one is the value of S1 and second one is the value of S2. So if we use these two values for the methods S1 and S2. First we'll see for the process P1 and then we'll move on to the process for P2. The options given here are, we have to check whether process P1 and process P2 are in a mutual exclusion state and they are in a progress state or they are not in a progress state. We have to find using these two methods. The first method for P1 is while S1 is equal to S2. We'll take the first condition. The first condition is 0, 0. Means here S1 is 0 and S2 is also 0. So 0 equal to 0 is a true. This means that the process P1 will be in a busy waiting state. It does not enter into the critical session because the condition says true. Next comes to the process called P2. Here P2, while S1 is not equal to S2. S1 value is 0 and S2 value is 0. Here 0 is not equal to 0. So what will happen here is the P2 process will enter into the critical session and then it updates the value of S1 is not equal to S2. It means that here this will enter into the critical, this will not enter into the critical session P1 whereas P2 will enter into the critical session. So this shows that the process will be allowed for mutual exclusion process. So we have find the first answer as exclusion, mutual exclusion process. And we have to check whether there is a progress in P1 and P2. For checking the progress in P1 and P2, we have to take the values as Boolean variable as I said earlier. For S1 and S2, we'll take 0, 0. we'll move on to the methods called P1 and P2. Here, the process P1 is ready to access, as process P2 is not ready for the execution. So here, the same condition happens here, S1 equal to S2. So here it does not enter into the critical session P1, whereas P2 is not ready to do this process, so it is in the waiting state. So in this situation, if this condition happens, then only the process P2 will enter into the critical region, so that the value of S1 and S2 will get changed over. It gets changed from 0 to 1 for S2. So when it does the process of P2, then only the value of 0 will become 1. So here in this one, since P2 is not interested to complete its process, so the progress of P2 is not improved. So the option for this fourth question is, here there will be a mutual exclusion between P1 and P2, but there is not a progress between the process called P1 and P2. That's it about this topic. Thank you all. We'll catch you in the next video. Thank you.